Today's session is about something fundamental to our success: blast furnace efficiency and productivity. We operate complex, high stakes equipment, and optimizing its performance is not just about best practice, it's about understanding why every measure works. We will explore the core drivers of high output, the critical role of raw material, how we manage the furnace internal dynamics, and critically, the hidden cost of inefficiency. This understanding empowers each of us to maximize our output, reduce waste, and ensure a sustainable future for our operation. A single modern furnace like Gwangyang number 1 can produce an astounding 16,000 ton of hot metal every single day. This immense output comes with immense responsibility. Our blast furnace system alone represents 60 to 70% of total cost of iron and steel product and consume 70% of the total energy in entire plant. Every decision we make directly impact this massive scale, making efficiency non-negotiable. So, how do we achieve and sustain such high productivity? It largely comes down to three interconnected factors: oxygen, blast volume, and pressure. Oxygen enrichment is a directly productivity multiplier. More oxygen means more coke gasified, which means more iron. Just a 1% increase in oxygen can raise our flame temperature by 40 and in between 40 to 50 degree Celsius. However, pushing oxygen too far can cool our top gas below 100 degrees centigrade, making the furnace less efficient. Blast volume is our primary driver. More blast means more coke burned, more iron produced. But these forces are constrained by pressure management. We cannot exceed our maximum differential pressure delta P max. Our burden descent become unstable. Interestingly, higher PCI rate can help us increase this delta P max, allowing for higher burden columns. Our goal is high productivity of over 2.4 tons of hot metal per cubic meter of inner volume per day, a benchmark made by world-class furnaces like Gwangyang number 1 at 2.9 ton per meter cube working volume per 24 hours. At the heart of high performance is our raw material quality and preparation. Experts agree the quality of our burden influences 70% of our blast furnace process efficiency. For ferrous burden, sinter and pellet are key. We need sinter with excellent strength and high shaft heating temperature characterized by low reduction disintegration. Otherwise, it breaks down into fines and choke the furnace. Pellet offer flexibility, but we must be wary of issues like swelling in acid pellet. Coke is our structured backbone. It remains solid, supportive the entire burden and providing pathway for gas flow. We target a minimum coke layer thickness of 15 centimeter in belly to ensure the crucial gas distribution, and critically fines our enemy. Materials less than 5 mm drastically reduce the permeability. We must be vigilant in stockyard management to minimize the fines and control moisture, as these factors directly impact burden quality and furnace stability. Inside this giant reactor, precision control of gas flow and temperature is paramount. The blast furnace is a highly efficient countercurrent system where hot gas rises and burden descent. Gas spend only 6 to 12 seconds inside, dropping from over 2000 degrees centigrade to 100 degrees centigrade, while the burden descent at 8 to 15 centimeter per minute. Our primary tool to direct gas flow is burden distribution, because gas like water always takes the path of least resistance. Crucially, we must ensure circumferential symmetry. Every tier and every section of the furnace must contribute equally. Deviation can lead to major losses. Remember, local temperature dictates our chemical reactions. We rely on gas for efficient reduction in the upper furnace at 600 to 1100 degrees centigrade. But at over 1100 degrees centigrade, direct reduction becomes highly endothermic, consuming immense heat and causing thermal fluctuation. Monitoring hot metal silicon and temperature allow us to track the hearth thermal state and react swiftly. Let's be clear about the ultimate impact. Our blast furnace, while essential, are significant contributor to global CO2 emissions. 1500 to 2000 kg per ton of steel, accounting for about 6% of worldwide CO2. Every unit of energy wasted directly add to this environmental footprint. Producing a ton of hot metal costs us roughly 16 gigajoule of energy. Critical, even minor operational inefficiencies like excessive moisture are silent thieves. Just an extra 10 gram of moisture per standard cubic meter of blast can increase our coke by more than 5 kg per ton hot metal and drop our flame by more than 42 degrees Celsius. For a 12,000 ton per day furnace, this means burning an additional of 63 tons of coke daily, costing an illustrative of 19,000 every 19,000 US dollar every single day. Beyond this direct cost, inefficiency manifests as thermal instability, reduced productivity, increased maintenance from tear damage, refractory wear, and costly downtime. Your vigilance and proactive measure directly translate into energy saving, reduced emissions, and millions on our bottom line. So let's master these challenges together.